In previous video, we understood what Agentic AI is. Now in Phase 2, we go deeper. We'll break down the architecture, memory, embeddings, vector databases, RAG, and multi-agent systems. By the end of this video, you'll understand how real Agentic AI systems are designed. Let's now look at the high-level architecture of an Agentic AI system. An agentic system is not just a language model generating text. It is a coordinated architecture of reasoning, planning, tools, and memory working together to achieve a goal. Think of it as an intelligent software system, not just a chatbot. Every agentic system starts with a goal. This goal may come from a user prompt, an API call, or even a scheduled event. For example, analyze last quarter's sales data and generate a summary report. This input becomes the objective the agent must solve. Next, the request moves into the reasoning engine, the large language model. The LLM does not immediately produce a final answer. Instead, it interprets the goal and determines what needs to be done. It decides, is this a single-step task? Or does this require multiple actions? Do I need external data? The LLM provides intelligence, but not execution. In more advanced systems, we introduce a planning layer. The planner decomposes a complex goal into smaller, manageable steps. For example, retrieve sales data, perform analysis, generate summary, send report via email. This is what transforms simple prompting into structured task execution. Now comes the most powerful part of Agentic AI, tools. Tools allow the agent to interact with the real world. This could include querying databases, calling REST APIs, updating a CRM, sending emails, executing workflows. Without tools, the LLM can only generate text. With tools, it can take action. Memory enables persistence. There are typically two types of memory. Short-term memory, which holds conversation context and task state. Long-term memory, often stored in vector databases, which retains historical knowledge and prior interactions. Memory ensures the agent doesn't start from zero every time. Finally, the agent interacts with external systems. These may include enterprise databases, document stores, SaaS platforms, or internal services. This is where real business value is created, when AI connects to operational systems. So at a high level, an agentic AI system follows this architecture. A goal enters the system. The LLM reasons about it. The planner breaks it into steps. Tools execute actions. Memory provides context. And external systems deliver real-world impact. This layered design is what enables autonomy, scalability, and reliability. Now here's the idea that turns an LLM into an agent, the agent loop. A chatbot answers once, an agent iterates, it thinks, takes an action, checks the result, and decides what to do next. That repeatable cycle is what enables autonomy. The agent loop is a feedback cycle. It usually looks like this: think, then plan, then act, then observe, then reflect, and repeat. Each loop moves the system closer to the goal. Step 1 is think. The LLM reads the goal and asks, what's the current state? What's missing? What do I need to know? This is where reasoning happens, but no external action yet. The output of think is typically what I believe, what I need, and what I should do next. Next is plan. Planning means breaking the goal into steps and choosing the next best action. Example: fetch the data, validate it, summarize results, generate the final response. The key point is, the agent doesn't guess blindly. It makes a structured plan, even if it's lightweight. Step 3 is act. This is where agents become powerful. Acting usually means calling a tool, query a database, call an API, search documents, run code, send an email. In modern agent frameworks, this is done through function calling or tool execution. So the agent is no longer only generating text, it's performing actions. Then comes observe. The agent receives the tool output. Maybe it's JSON, a list of records, a document excerpt, or an error message. And this part matters. The agent doesn't assume the action worked. It reads the result like feedback from the real world. Now the agent reflects. It asks, did I get what I needed? Is the output valid? What's the next action? Reflection typically leads to one of 3 decisions: finish, goal achieved; continue, do the next step; recover, handle errors, retry, or choose a different tool. That recovery behavior is a big reason agents outperform single-shot prompts in real workflows. Let's make this real with a quick example. Goal: create a weekly status report and email it to the team. Think: what data do I need? Plan. Pull updates from Jira, summarize, format, email. Act. Call Jira API. Observe. Receive ticket updates. Reflect. Missing one project, fetch again. Act. Generate report. Observe. Draft created. Reflect. Send email. That's the agent loop in action. So the agent loop is the operational engine of agentic AI. A chatbot answers once. An agent loops until the job is done, using tools, reading results, and adapting. In the next section, we'll connect this directly to memory, because memory is what makes the loop smarter over time. Memory is what transforms an agent from reactive to intelligent. Without memory, every loop starts from zero. The agent forgets previous actions, prior context, and historical interactions. With memory, the agent accumulates knowledge, across steps and even across sessions. In practical terms, memory enables continuity, personalization, and smarter decision-making. In agentic AI, memory is not optional, it is foundational. Short-term memory is often called working memory. It includes current conversation history, intermediate tool outputs, task progress state, scratchpad reasoning. This memory exists within the active loop. It helps the agent reason step by step without losing context. Long-term memory is persistent across sessions. It may include historical interactions, domain knowledge, user preferences, previously solved tasks. In modern systems, long-term memory is often stored in a vector database using embeddings. Let's look at how long-term memory works technically. Step 1. Important information is converted into embeddings, numerical representations of meaning. Step 2. These embeddings are stored in a vector database. Step 3. When a new query arrives, it is also converted into an embedding. Step 4. The system performs similarity search to retrieve the most relevant past memories. Step 5. Those retrieved memories are injected back into the prompt context. The agent now reasons with both the current input and relevant historical knowledge. Memory interacts with the agent loop in two ways. During each loop iteration, short-term memory tracks state. Across multiple sessions, long-term memory enriches reasoning. So the agent doesn't just think, it thinks with experience. In production systems, memory design raises important architectural questions. What should be stored? What should be forgotten? How do we manage token limits? How do we prevent stale or incorrect memory from influencing decisions? Poor memory design can degrade performance or introduce hallucinations. Good memory design improves precision, personalization, and efficiency. Embeddings are numerical representations of meaning. They convert text, or other data like images, into high-dimensional vectors. Instead of understanding language as words, machines represent meaning as coordinates in mathematical space. If two pieces of text are semantically similar, their vectors will be close together in that space. In simple terms, embeddings allow machines to measure meaning. An embedding is simply an array of floating point numbers. Modern embedding models typically produce vectors with hundreds or thousands of dimensions. Each dimension captures some latent semantic property learned during training. We don't manually interpret each number, but together, they encode meaning in a structured way. Embeddings are not keywords, they are mathematical encodings of semantic relationships. Embeddings are generated by specialized neural networks trained on massive corpora of text. During training, the model learns patterns of language, which words co-occur, which concepts relate, and how context changes meaning. The output layer of that model becomes the embedding representation. So when you pass in a sentence, the model compresses its meaning into a dense vector. These embedding models are different from generative LLMs. They are optimized for semantic representation, not text generation. In agentic AI systems, embeddings power three critical capabilities: semantic search, memory retrieval, context injection. When an agent needs knowledge, it converts a query into an embedding. It then performs similarity search against stored vectors to retrieve the most relevant information. That retrieved content is injected back into the prompt, enabling more informed reasoning. Embeddings are the bridge between unstructured data and intelligent reasoning. Similarity between embeddings is typically measured using cosine similarity or Euclidean distance. If two vectors point in similar directions, they represent similar meanings. This allows systems to retrieve information based on meaning, not exact keyword matches. Example. Query. How do I insure my pet? Matches documents about pet coverage, veterinary insurance, animal protection policies, even if exact wording differs. In enterprise systems, embeddings allow organizations to unlock value from policy documents, knowledge bases, support tickets, email archives, CRM notes. Instead of rigid keyword search, embeddings enable intelligent retrieval across large unstructured datasets. This is why embeddings are foundational to RAG pipelines and memory systems in modern AI architectures. But embeddings alone are not enough. Once we convert text into vectors, we need an efficient way to store and search them at scale. That's where vector databases come in. Once we convert text into embeddings, we face a new challenge. These embeddings are high-dimensional vectors, not strings. Traditional databases are optimized for structured queries, exact matches, filtering, sorting, but they are not optimized for semantic similarity search across millions of vectors. That's where vector databases come in. Vector databases are purpose-built systems designed to store and efficiently search embedding vectors. A vector database stores high-dimensional vectors along with associated metadata. Each entry typically contains the embedding vector, original text or document reference, metadata such as source, timestamp, category. The key difference is how retrieval works. Instead of querying by keywords, we query by similarity. You don't ask, find documents with this word. You ask, find vectors most similar to this vector. When a new query arrives, Step 1. Convert the query into an embedding. Step 2. Compare that vector against stored vectors. Step 3. Compute similarity using measures like cosine similarity or Euclidean distance. Step 4. Return the top k closest matches. This process is called nearest neighbor search. The database retrieves meaning, not matching words. Searching through millions of high-dimensional vectors naively would be computationally expensive. Vector databases use specialized indexing algorithms such as approximate nearest neighbor and HNSW, hierarchical navigable small world graphs, IVF, inverted file index. These structures allow similarity search to run in milliseconds, even at scale. The goal is to balance accuracy and speed. In retrieval-augmented generation systems, vector databases are the retrieval backbone. When the agent needs knowledge, it embeds the query, retrieves relevant documents from the vector store, injects them into the prompt. This enables context-aware reasoning. In agentic systems, vector databases often power long-term memory. Embeddings give us meaning. Vector databases give us scalable access to that meaning. In production systems, vector database design raises important architectural decisions. How large are the embeddings? How often do we update them? How do we handle versioning? How do we manage data freshness? How do we secure sensitive information? Vector search is powerful, but governance, monitoring, and indexing strategy matter. Notice, the system may retrieve documents that don't contain the exact same phrasing. That's semantic retrieval in action. Let's define retrieval-augmented generation, or RAG. RAG enhances a language model by retrieving relevant documents before generating a response. The flow is typically: convert the query into an embedding, retrieve similar documents from a vector database, inject those documents into the prompt, generate the final answer. The purpose of RAG is to ground the model in external knowledge. RAG improves factual accuracy and domain specificity, but it remains a single retrieval and response cycle. Architecturally, the difference is structural. RAG is linear. Agentic systems are iterative. RAG retrieves knowledge. Agentic systems coordinate reasoning and action. RAG answers better. Agents accomplish goals. Importantly, RAG and agentic systems are not competing approaches. In many real architectures, RAG becomes a component inside an agentic system. The agent may use retrieval as one of its tools. So the relationship is hierarchical. RAG augments knowledge. Agents orchestrate knowledge and action. In a single agent system, one agent handles reasoning, planning, and tool execution. All decisions flow through a single intelligence unit. The architecture is centralized and simpler to manage. Benefits: easier to build, easier to debug, lower coordination complexity, good for moderate workflows. Limitation: becomes cognitively overloaded with complex tasks. In multi-agent systems, responsibilities are distributed across specialized agents. For example, one agent gathers data, another analyzes, another validates, another executes. Coordination may be managed by a supervisor or orchestrator agent. Multi-agent systems introduce modular intelligence. Multi-agent systems improve specialization and scalability, but increase orchestration and monitoring complexity. In this video, we covered architecture, agent loops, memory, embeddings, vector databases, and how RAG compares to agentic systems. In the next video, we move into execution and orchestration, planning and reasoning, tool calling, autonomous loops, guardrails, and observability. If this series is helping you, please like the video, subscribe, and share your thoughts in the comments. Thank you for watching.